synthesize your application code from test suites without actually having to interact with a real hypervisor. And that's used to quite a high degree of success in the Vert Manager application and some of our other command line tools like Vert install. So that's worth looking at if you're looking at a way to test things. From the KVM user's point of view, things are a little bit more complicated. Each QEMU instance only knows about itself. So we want something that knows about the state of the host as a whole. And that's where the Libvirt daemon comes into play. So the application talks to the Libvirt library, which goes out to our generic RPC system. This talks to the Libvirt daemon, and that's where the QEMU driver, or the Linux container driver, or user mode Linux, or the modern Xen driver, they all live in the Libvirt daemon. And from the Libvirt daemon, we then talk to the underlying hypervisor technology. So in the KVM case, we talk to QEMU. So the Libvirt daemon is maintaining all of the persistent state about the hypervisor host in this architecture. So now I want to just move straight on to some of the some of the interesting features we've implemented in Libvirt or the Libvirt daemon that do things that are useful for KVM, which KVM can't or won't do itself. So disk access protection. People generally get a little bit unhappy if they have two VMs pointing to the same disk image and they boot them both at the same time, because they tend to lose all of their data. QEMU doesn't do anything to protect against this. You pass it a disk, QEMU will happily run against that disk. It doesn't have any awareness of any other virtual machines that are running on that host or any other hosts. So QEMU alone has no way to offer disk protection directly. As well as the case of two different guests being pointing at the same disk image, you might have the same disk, so the same guest configuration visible to multiple hosts. And you don't want to risk starting that same guest on two different hosts at once, because again, bad stuff will happen if you're not using a cluster file system in your disks. So Libvirt provides 3 disk access modes when you're configuring the guest. You can have read-only shared mode. All the guests get a read-only view of the disk, so they can't do any writes to it. This is useful if you have a CD ISO image, typically. The read-write shared mode. This is intended to cope with the cluster file system scenario. So if you want to run GFS or OCFS, you typically have SAN storage that is made visible to multiple hosts, and then multiple virtual machines can all access the same run. And as long as they're using a cluster file system, that's all perfectly safe. The last disk access mode, which is actually the default one, is read-only exclusive mode. And this is what you want to use if you've got a disk image that is only intended for use by a single guest at any time. And as I say, this is the default. And I say these read-only shared, read-write shared, and read-write exclusive. One of the things we've liked to keep quiet over the years is the fact that Libvirt does actually really enforce these different sharing modes. It's really, we've been relying on the management application using Libvirt not to do stupid things. We've only enforced them by accident, by virtue of using SELinux for labeling disk images. So if you had a read-write exclusive disk and you label it for one VM, then if you tried to start a second VM, it would get relabeled, and then SELinux would block all writes from the first VM. So we kind of had mutual exclusion by accident by virtue of using SELinux, and that obviously wasn't the ideal situation to be in. So over the past probably 2 years, in fact, we've developed a disk locking mechanism inside Libvirt. And this disk locking mechanism is pluggable. So we have two implementations. The first implementation we did made use of a technology called sandlock. And this sandlock project came out of some work that the Vert developers did. They developed this algorithm for disk access locking that is based on the disk Paxos algorithm. And this is really, they targeted this towards SAN deployments. So if you have fiber channel adapters exposed to your virtualization hosts, and then virtual machines are using LUNs on that fiber channel adapter, that's the kind of scenario they designed this for. And sandlock runs as a separate daemon, and Libvirt asks sandlock to take an exclusive lease, and that lease represents a particular disk image. So sandlock will acquire the lease, and once that lease is acquired, then Libvirt knows it is safe to start this virtual machine. And if at any time the lease is lost, for example due to the SAN storage going AWOL for whatever reason, then sandlock has the ability to fence the virtual machine. So this is useful if the SAN goes missing on one host, and you want to fail over that VM to a second host, and you want to actually make sure that the VM on the original host has gone away. So you want sandlock to kill the VM on the original host before it allows the lease to be acquired on the new host. There are really two ways that we use sandlock in Libvirt. I call them the manual lease method and the automatic lease method. In the manual lease method, the management application, such as Vert or OpenStack, is responsible for deciding what leases need to be associated with what VMs. And the management application can use these leases for representing any type of mutual exclusion. It's not restricted to doing it for disk images. So if you have IP addresses you're assigning to individual hosts, the management application can say, well, I want to have a lease for this VM that represents the IP address that I'm going to assign it. But the more common cases, you give it a lease for each virtual disk that you're giving it. And so in that case, the management application is in total control of the leases. Libvirt doesn't care what the leases represent. It just knows that this VM has this many leases, and all of the leases must be acquired before the VM is allowed to start. This is very flexible and very powerful, but it also has a bit of an administrative burden. So we introduced a simpler way of using sandlock, which is the automatic lease method. And in this case, Libvirt just creates leases based on the MD5 checksum of the disk path. Now obviously this has some limitations. You've got to make sure that if your disk images are visible via a number of different paths, for example, if you're using a block device, it may be visible as dev SDA, and it may also be visible as dev disk by UUID, some big long string. So you've got to make sure you're configuring your VMs using a consistent file path for the automatic lease method to be safe. But that's probably good enough for many use cases. So we provide this automatic lease method in Libvirt. The only other caveat is that since we did this, the sandlock guys have decided they don't really want sandlock doing leases on file systems. They really want it to only work on raw block devices. So they don't much like us doing our leases on shared file systems like NFS, but it works anyway, despite them not liking it very much. Sandlock is great, but one of the downsides of sandlock is that the disk Paxos algorithm has a pretty high I/O overhead. So you've got to have storage. The storage that's holding your leases has to be capable of sustaining fairly high data rates, and you may not want to have all this disk I/O bandwidth consumed just by leases. So we introduced a second lock manager plugin in Libvirt, and this is known as the Vert Lochte plugin. And this is included by default with Libvirt. So any Libvirt in the last probably 4 to 6 months has this capability included in it. And this just takes logs using the fcntl system call and the locking capabilities that provides. As such, it obviously requires use of a shared file system, and a shared file system which actually supports fcntl locking. There are some shared file systems which don't support this locking mechanism. I think OCFS is one of the ones that doesn't support it in all possible configurations, but I don't use OCFS, so I mean, I don't really care, but some people might care. At the moment, the Vert Lochte plugin is based exclusively around the idea of automatic lease management. So we have several ways of actually doing the automatic leases. The simplest way is direct file path. So if you have a disk image you've given to your guest in var libvirt images myguest.qcal, it will actually take a lease directly on that file, which is all right for files that are on a shared file system. But if you're using a SAN storage, you've got a device node in /dev. And you can take a lock on that device node in /dev using fcntl. That lock's only going to be visible to one host, so that's not very good protection. So we introduced a couple of alternative ways of acquiring the leases. The second way is just to do it based on a SHA-256 checksum of the file path. So if your block device is visible using the same path on each host, then that gives you mutual exclusion. But again, you've still got the problem that there are several different block devices can appear in the Linux file system with several different names. And we wanted to have a way to acquire leases which was safe regardless of which file path you used for the block device. So we added a way to acquire leases based on either the LVM UUID, and if you're using cluster LVM, this UUID is guaranteed to be the same on all hosts which see that LVM volume. Or similarly, SCSI volumes have a unique ID associated with them. So if you have a SAN volume that is visible on multiple hosts, that unique ID is visible in the same way on all hosts. So we acquire leases based on those unique identifiers. So that's the second way you can do disk locking in Libvirt. One of the enhancements we'd like to do is to introduce a way to use the Vert Lochte mechanism for completely arbitrary leases, so that the management application has complete control over how and where the leases are acquired. So in the same way that you have the manual lease mechanism with SANlock, we want to add that to Vert Lochte. So I think the takeaway point for this is if you're writing a management application with Libvirt, then you want to have safety guarantees that your VMs are not going to use the same disk image at the same time. Then you want to be using, you want to be configuring your hosts to enable the Libvirt Lock Manager plugins for QEMU. This is just a quick illustration of the architecture of the Vert Lochte plugin. We've got the same general architecture across the middle here. And then the QEMU driver actually speaks via an RPC protocol to a separate Vert Lochte daemon. The reason we did this in a separate daemon is twofold. We want to be able to restart the libvirt daemon whilst VMs are running without having any impact on them. We want to do this so that we can deploy RPM upgrades and then restart libvirt to actually activate the new code. But when you're restarting the daemon, you don't want to lose all of your leases, because that's a safety problem. So we decided to split the lease functionality out into a separate Lochte daemon. And the way this deals with upgrades is that it's capable of re-execing itself whilst holding open all of the file descriptors associated with the locks that it holds. And it's only possible to do this re-exec glance when you have a very narrowly targeted set of functionality you're trying to preserve across the exec. So it had to be in a separate daemon. The second reason it had to be in a separate daemon is because the POSIX API for locking is incredibly, utterly, brain-deadly stupid. If you have a file open, and you have that file open multiple times, so you have, say, 4 file descriptors pointing to the same file, you acquire a lock on this file descriptor. If you close any of those other file descriptors, it's going to release all of your locks. I can't express how unhappy this makes me with the POSIX API. It makes this FCNTL locking absolutely horrible to use. The only way to do it safely is to have a dedicated process just for dealing with locks, where you can guarantee that no other library call you're making is going to be secretly opening the file that you're locking behind your back. So enough about locking. Let's move on to something else. This is a feature that has been requested by users for many years. People have been requesting this for at least 5 years, if not more. And over this past year, we finally got around to implementing it. So for those who have used Libvirt before, you'll know there's basically 2 privilege levels in Libvirt. You can have, if you connect to Libvirt, your connection can either be in read-only mode, where you're allowed to do any APIs that query information about guests or what's going on in the system, or you can have read-write mode, where you're allowed to do absolutely anything that Libvirt allows you to do. And that's fairly crude. There's a number of cases where you might want to have a privilege level that's somewhere in between those 2 cases. So we introduced the fine-grained ACLs capability. I think we introduced this in the Libvirt 1.1.0 release. And this allows you to set up permissions on a triple of the object, such as the virtual machine or network or storage pool, the subject, which is the user or application that's using Libvirt, and a permission, such as boot, shutdown, save XML, or so forth. So now you can express rules such as allow Frank to start the guest Apache. So he is much more, you can give him access to do write operations in a much more constrained way. And this mechanism has been wired up across all of the Libvirt public APIs. So if you look in the API documentation for Libvirt now, against every API, there will be a little bit of documentation which tells you what permission check is done for that API. Some APIs have multiple permission checks. For example, if there are flags that control the behavior of the API, some of those flags may imply an extra permission check is performed. And these permission checks are done for all of the virtualization drivers which run inside the Libvirt daemon. So that means these permission checks are useful for KVM, LXC, user mode Linux, or the modern Xen driver. We don't attempt to do any permission checks for the drivers that run entirely client-side, such as the ESX driver or Hyper-V, because that's really pretty pointless. Libvirt, if the Libvirt client library did a permission check which denied you access to the ESX server host, well, you just go around it and talk to the ESX host directly. So we only do permission checks for drivers where Libvirt is actually managing the state of the host. And this mechanism is again pluggable, because while we had an idea of what permissioning implementation we wanted to use, we didn't want to lock ourselves into one particular technology. So to start off with, we've integrated with PolicyKit. PolicyKit is a fairly commonly found authorization framework in modern Linux systems. It's more commonly found in a desktop environment, but as it's designed, it's in no way tied to desktop Linux usage. It's equally applicable to any server virtualization or server usage of Linux hosts. So The first and currently only access control plugin for Libvirt is based on PolicyKit. And we have a mechanism for mapping the Libvirt permissions and Libvirt object types to PolicyKit actions. So if you have a start permission on a domain object, this gets mapped into an action called org libvirt API domain.start. And again, there's web pages that are linked to from the Libvirt API documentation, which tell you what all of these PolicyKit action names are called. So you can look up what actions are implied for a particular API call. To represent the object being affected by the operation, we pass through one or more pieces of identifying information. So we pass through the driver name, which is basically what virtualization driver this is, so whether it's QEMU, LXC, user mode Linux, or Xen. In the case of virtual domains, we pass through the ID. When you start a virtual guest, it gets assigned a unique integer ID for as long as it is running, so that's one way of identifying guests. Guests also have a unique UUID, or they have a slightly more friendly name. So those are the 4 attributes we provide for virtual domains. Other object types in Libvirt have different unique identifiers associated with them. And again, the online documentation tells you what unique identifiers you can rely on for each type of object in Libvirt. One thing that is slightly limited in our current implementation is how we expose details about the user. This is really a limitation of PolicyKit itself. In the back end for PolicyKit, it really only knows about local Unix users. So if you're a local application connecting to Libvirt locally, you've got a Unix user ID, a group ID, and a process ID that's associated with you, and that's provided to PolicyKit for doing permissions checks. You might ask, what if you're connecting to Libvirt remotely over TCP? You're not going to have a local Unix user ID, at least not one that we can trust. But when you connect to Libvirt remotely, you have to authenticate with Libvirt using either an X509 certificate, which has every X509 certificate has a unique distinguished name associated with it, so that can identify the client user. Or if you're authenticating using SASL and Kerberos, you have a Kerberos principal name. So one of the things we want to do in the near future is pass through information about the SASL username or Kerberos principal name or certificate distinguished name. So then you'll be able to use that information to identify the client application when writing access control rules. People at the back probably can't see this, but I just wanted to give a quick illustration of how you might write an access control check for Libvirt. Judging by people at the front squinting, they probably can't see it either. But I'll describe it anyway, so it doesn't matter if you can't really see it. PolicyKit, as it exists for the past year or so, uses a JavaScript backend for doing access control checks. Previously, it was just a plain ini-style text file, but that's not really flexible enough for doing some of these fine-grained access control checks. And you might want to integrate with an external directory service of some kind. So they introduced this idea of a JavaScript backend to PolicyKit. So now as an administrator on the host, if you want to set up access control rules, you have to write short JavaScript code fragments. And the unique identifiers about the object, the user, and the permission are made available to this JavaScript runtime. So you can do things like set up a rule. In this case, I've set up a rule saying if the operation being performed is org libvirt API domain.getAttra, and this just is a basic query for information about domain, and the user asking for it is Béranger, and the action and the action object has a driver name of LXC, and the guest name is demo, then allow that user access, otherwise deny them. So this is fairly powerful, but at the same time, it's probably going to be quite tedious to write these rules if you have a lot of very different and complex rules you're trying to set up. So this is really a first step towards future enhancements to kind of try and make this work easier. As I said just a few minutes ago, one of the ideas of using JavaScript is that you'd be able to integrate with external systems. So if you had, say, a directory server or a NIST database or something which provided records about access control, you could write some JavaScript to talk to that directory service to query your access control rules, and that would provide you a way to centralize all your access control rules in one place. So that's something that is yet to be explored, really. We've got the basic access control framework in Libvirt, but there's clearly a lot more to be done or experimented with to find out ways to make this more manageable.
Do we want to actually add in the Libvirt API the APIs to actually manage the rules? Do we always want to offload that?
Yeah, I mean, the main point of actually using PolicyKit is that this gives us clean separation between Libvirt, which is doing all the operations, and the access control mechanism. So we wanted the actual access control mechanism to be completely pluggable and separated from Libvirt, so that people can write custom backends for PolicyKit to do whatever integration they might want to do and not have to modify Libvirt each time they come up with a new way they want to do access control. So Libvirt simply makes the query saying, am I allowed to do this on this object? And then the actual decision making is handled by an external component. So I'm going to move on to the next topic now, which is SELinux. SELinux has been around in Libvirt for quite a long time, often referred to as sVirt. And the way this works by default is that each virtual machine you start gets assigned a unique MCS category, and that's paired with a label like sVirt-T, or more recently sVirt-TCGT. And that label will is uniquely assigned to one guest instance, and it gives you mandatory access control between each instance. So that even if there's a compromise of QEMU, SELinux is going to confine that, so it's not going to be able to access any resources other than those that it already had access to. As well as the automatic way of assigning SELinux labels, there was a manual way where the management application had complete control over the label. That was very good for flexibility, but it put a bit too much of a burden on the management application. So we introduced a third way, where you just specify the base label. For example, you might have a custom my sVirt-T domain type, and you still want Libvirt to dynamically assign the categories. So we introduced that third way of configuring SELinux. And another flexibility thing we added was the ability to override this for individual disk images. So for example, if you had an ISO image that was on read-only storage and you don't want Libvirt to try relabeling that ISO image, you now have the option to turn off labeling just for that individual image. We also expanded sVirt to cover discretionary access control. Libvirt has always been for a long time, Libvirt's been able to run QEMU instances under a dedicated QEMU user and group account. But all QEMU instances were running under the same user account, so there's no separation between them. This only protected the host from a guest, it didn't protect guests from each other. So we incorporated discretionary access control into sVirt. So now you can assign a unique user ID to each individual guest. So they'll be separated from each other using discretionary access control. So this is just another line of defense if you're not using SELinux for whatever reason. And again, we made it possible to control this on a per disk image basis. Audit logging. This is something that's been around for a little while in Libvirt now, but possibly not many people are aware of it. In the QEMU and Linux container drivers in Libvirt, anytime an operation is performed that has some relation to host resources, such as starting a guest or hot plugging a disk or attaching a PCI device, we generate a formal audit log. And this gets fed into the kernel's audit subsystem and persisted somewhere by the audit daemon. So this gives you an audit trail of what operations have been performed on guests on that host. This work originated with government requirements for common criteria certification, but we can see that this audit trail can be useful to many other users who just want to know what's been going on with their virtualization hosts. This is more of a developer relevant feature at the moment. Libvirt has extensive debugging capabilities, and historically we've just sent a message out to syslog, which is as great as syslog is, which is not very great, but it's just a plain formatted text message. Some people try to define a structured syslog where you send JSON documents into syslog, but very few people find that appealing, because the nice thing about syslog is it's plain text, and now you're filling it with JSON documents. That's throwing away the only advantage of syslog. Unfortunately, systemd came along and invented this thing called the journal, and the journal is actually really, really nice to use from a client application, because it allows you to do structured logging, where you have individual data fields for each item you want to log. And even better than this, the way the communications protocol happens with the journal, you can send all of this structured data to the journal with zero copy overhead of your data, which is not something you can do when you're formatting strings for syslog or building up JSON strings for structured syslog. This is a nice way to minimize the overhead of debug logging and still get nice structured logging. This is probably one of the most frequently requested features for Libvirt, the ability to control the cgroups layout. If any of you have looked at the way Libvirt does cgroups in the past, you'll know that it's had a very fixed layout, which was three levels deep. You'd create a Libvirt directory, then we'd create a KVM directory, then we'd create a directory for each individual guest. This was done back in the days when cgroups was very new. No one really knew how it was going to be used, so we just picked some arbitrary layout. And it turns out this is bad for a variety of reasons. The thing that really hit us first of all was the fact that for a long time the kernel cgroups has been horrifically not scalable. So if you created deep hierarchies where they would say 3 or 4 levels deep, then kernel performance would just plummet. Or if you had just a large number of cgroups and big SMP machines, then the scheduler performance would plummet. So we made an effort to simplify the Libvirt layout, mostly by flattening it out, which was the biggest performance benefit. The other performance problems have been addressed in the kernel to a large degree. So now there's just 2 levels by default. At the very top level, we'll create a directory called machine, and then under that we'll create a directory for each virtual machine. If you're using systemd, things are a little bit different, because systemd wants to be in charge of creating all the cgroups and defining its own naming convention. So the cgroup will be called machine.slice, but the actual broad functionality is the same in both cases. It's just a slightly different naming convention if you're using systemd on your hosts. So you think, well, that's still a fixed hierarchy defined by Libvirt. That's only half the problem solved. So we introduced a new bit of syntax into the configuration for guests, where you can specify the name of a resource partition. So in this case, I've specified a name of machine/production. And this gets mapped through into a cgroup directory. In the non-systemd case, it's /machine/machine.partition. In systemd case, there's a slightly different naming convention. It has .slice on the end of things. Again, that's just a systemd quirk. But the upshot is that you can now define arbitrary groups of your virtual machines with arbitrary hierarchies that you're in complete control over. So you can put all of your virtual machines at the very top level if you want, or you can create a 10-level deep hierarchy, or anything in between. Libvirt doesn't constrain you in any way anymore. So that should be quite useful for people wanting to try out different ways of grouping and managing their SLAs for virtual machines.
What release were those changes made? The new style? Is it?
I am afraid I can't exactly remember, but it's the non-systemd stuff came in along first, and then a release or two later we added the systemd stuff. So it's probably the last 4 or 5 releases that the stuff started to appear in. I think Fedora 20 definitely has it all. Rel 7 will have all this. So it's fairly new stuff still.
Did someone did any performance tests to the new layout?
Performance tests are ongoing. We just know from previous performance tests we do that the depth of the hierarchy is a real killer. So the fact that we've reduced the hierarchy by at least 2 levels, we already know that's going to give us a good performance win. We don't know the exact quantity of that performance benefit, but we have, at least in the RHEL side of things, we have a performance team who is analyzing this on an ongoing basis and looking not just at what Libvirt does, but also what the kernel does.
So the key issue is the hierarchy?
The hierarchy was the key issue. The total number of groups was another issue. That's been solved by the kernel because it's the only real place you can solve that. So the last few slides, I just want to mention some of the resource tunables you have with Libvirt. Some, but not all of these, are done using cgroups. The scheduler tunables are done using cgroups. So you have the first one is simple CPU shares. This is just a relative weighting of virtual machines. Slightly more interesting is some absolute time slice, where you can specify the period and quota assigned to each individual vCPU thread in QEMU, as well as the non-vCPU threads. CPU models, you can choose a number of different ways to configure the CPU with QEMU, either by a named model, or by copying the host model, or by doing actual host CPU pass-through explicitly. Tuning memory. There are quite a few NUMA options in there now. You can control the placement of individual vCPU threads. You can control the placement of non-vCPU threads. You can control what NUMA nodes memory is allocated from. And you can do all this statically, or Libvirt now is able to talk to a process called NUMAD, and NUMAD will tell Libvirt, well, this NUMA node seems to have a good set of resources free, place the VM on that NUMA node. So you get a bit of automatic NUMA placement there, which helps the overall utilization of your NUMA system, although it's by no means perfect. And you can also set up NUMA topology inside the guest. But to be honest, that's not particularly useful at the moment because you really want to be able to map the NUMA topology in the guest through to the NUMA topology in the host. And that's an area of active discussion in the QEMU community at the moment. There's a number of flags for controlling aspects of memory allocation. So you can say whether you want explicit huge pages, whether you want to allow memory sharing by the KSM daemon, and whether you want the guest memory to be locked into RAM, so prevent swapping of the guest. And the last thing, there's a few memory tunables that we implement using cgroups. So you can set soft limits, hard limits, minimum guarantees, limits on the amount of swap you can consume, and a few other things that cgroups exposes. Question at the back?
Question about the minimum guaranteed memory. I mean, last time we checked with your Brno Libvirt guys, it wasn't even used anywhere in the KVM code. So it was used for S6, I think, or A6, but it wasn't used for KVM. So because we used that stanza in the XML,
Yeah.
it wasn't used by Libvirt. So is it changing now, or what's the actual semantic?
I'm not sure, to be honest. I'd have to look into that, because I've not worked on that area of the code recently, I'm afraid. Just a couple more slides, as we're basically out of time here, actually. There's tunables for the block devices. There's some per guest level tunables, which we implement using cgroups. And then there's per virtual disk tunables, which we implement using QEMU's IO limiting for its virtual disks. And we've got tuning of network interfaces. We don't use cgroups for this either, because you really want your network tunables to be set on a per virtual interface. So Libvirt directly uses the traffic classifier facilities in Linux to attach policies to the individual tap devices. And of course, you've got limits on the amount of bandwidth migration can use. And that's it really. It's a brief whirlwind tour of some of the lesser known Libvirt features, which I hope you found useful. That's a lot. I think we're out of time for questions as well, so if you've got any questions, come and see me afterwards separately. And help yourself to any stickers at the front or back of the room.